Good morning. Welcome to this morning's webinar from Smart Vision. I am just going to give this a moment or two, mostly to check that I've pressed all the right buttons and that I've got people joining correctly from the waiting room, which I see that we do. Okay. So our session this morning, we're talking about model building for optimization and efficiency. My name's Rachel. I'm mostly in the background, covering questions and making sure people are logged in correctly. Our two presenters today are John McConnell and Robert Cordina. John, you are going to kick this off, I think. So
I am
I'll
indeed.
hand it over to
Yes.
you.
Thank you, Rachel. And Robert, you're driving, so I'm going to just say next slide at the right moment. So next slide, please, Robert. Thank you. Thanks, everybody, for joining. Just to start with some housekeeping, we are recording this session, so I hope that's okay for everybody. At the end of it, we will share the slides with you, and we are open to discuss further conversations with colleagues. We can rerun. We can have specific versions that are more tailored to your requirements if that's appropriate. In terms of questions, in sort of standard webinar style, please could you pop them in the chat? So we can't hear anybody, but if you pop questions in the chat, we'll look to address them as soon as we can, and we'll get back to you with answers. Next slide, please, Robert. Just a little bit before we get into the meat of it about who Smart Vision are. As you can see, we have some partnerships. I think many people on the call will know us as the SPSS people. Smart Vision people all at one time or another were SPSS, work for SPSS. These days, we're a bit broader than that. We partner with a variety of big and small players, like Amazon and Funis, which is Robert's company, Open Scoring, which is a European specialist in PMML and model transfer. We're not just commercial anymore. We do a lot of work with open source, and you'll see some examples of open source today. So lots of work with Python and R. We are the folks who do statistics, data science, etc. We've been doing it for a long time, and we do it, across sectors and geographies. And there's a little bit at the end about, how we do it in terms of how we deliver. But at that point, I'm going to hand over to Robert. Robert, would you like to just introduce yourself before we get into the core of the presentation, please?
Yeah, hi. So hi, everyone. My name is Robert Cordina. I am from Funis Consulting. My background is in pharmaceuticals and the food industry. I have a good number of years of experience in modeling and simulation, both in data-driven models, so data-based models, as well as physics-based models. And I am particularly interested in optimization, and we'll be discussing a bit more today of what that means or could be for yourselves as well. And I am partnering with Smart Vision Europe for this webinar and for any work that would come in the future. And I'm really excited to be here.
Thanks, Robert. Over to you.
All right. Okay, so today's agenda is what is optimization and what types of optimization can be done. We'll be spending a few minutes on that. And then the meat of the presentation release, we have a couple of examples that I will demo to really explain what kind of opportunities optimization can offer. And then John will round off on what areas these can be applied to and how to access these optimizations easily. So let's kick off with a background of what optimization is. But actually, before we do that, we need to take a small step back and actually start with predictive modeling. So in predictive modeling, as I am sure all of you are aware, we know what X is, we know what our input is, we know the relationship between X and Y, what is called the function of X, or f of X, which we then use to calculate the output Y, right? So in this case, we know the first two boxes and want to find out what is in the third box, what is our output Y. Now, the simplest example of this is the straight line relationship, y equals mx plus c, right? So the blue line in this plot. So the f of x is equal to x plus 1.5. And this could actually start getting a bit more complex, such as in the orange line, which has a quadratic equation, right? But it can be extremely complex than this, where we don't have a single input x, for example, but we have any number of inputs. Or an f of x can be a very complex set of equations. But as long as we know what the f of x is, then we can calculate or predict what y will be. Now, optimization works differently, where we know what we want to get to. That's the desired output y, right? But we either don't know what we need to get there, that is what the input x should be, or we do know what our starting point x is. We know what we want to get out, that is y, but we don't know how to get there. That is, we don't know what the f of x is. So in both cases, we are using what we do know, so the blue boxes here in this case, to try and find out what we don't know, right? So that's the purple boxes. Now, actually, why is it actually called optimization? So in any optimization process, we have to have an objective function, sometimes also referred to as a loss function or a cost function, which you might have heard. So this is pretty much the simplest objective function you can have, right? So I know what my desired y is, what my objective y is. So when I use a specific value of input x, given that I know f of x, I can calculate what y will be, right? We've seen this. So from this, I can calculate a loss value or a cost value. And this is simply the difference between what I want to get, my objective, and what I am getting given my current input x. So by iterating and changing x over several values, I keep predicting what y will be until my loss value is the smallest I can achieve. That is, I am optimizing my value of x to achieve the y that I am after, hence the broader field of optimization. So what we want to end up with is something like this, right? Where with an increasing number of iterations, as you can see here on the x-axis, with more values of x that we try, we eventually reach zero loss. So in this case, my predicted will be the exact same value as my desired value of y, right? So we go from guessing what x could be, right, to knowing what the value of x should be to achieve the exact value of y that I want. Now, there are various types of optimization problems, right? For example, you can have a single objective optimization problem, such as you want to match a single value or minimize cost or maximize profit, but not at the same time, right? Or you can have a multi-objective optimization where you want to minimize cost and time or maximize profit while minimizing the number of people on your payroll, for example, or you want to match several output values. And so the number of objectives can really be whatever you want it to be. But of course, if the more objectives that you have, with an increasing number of objectives, comes increasing complexity and a reduced chance of getting zero loss or finding the global minimum of your system. The model type, your f of x, so to speak, can also take different forms, generally classified as linear or non-linear, which means that they can range from very simple, y equals mx plus c, which we're all very familiar with, to something extremely complex, differential equations, non-linear equations, and so on and so forth. So further to this, there are two main things which can make optimization difficult. And these are conflicting objectives and constraints. So in this case, what I would like to find is the right balance between cost and time for my sorting process. So as you can imagine, the more people I have to sort whatever I am sorting the less time the process will take, but it will cost me more as I need to pay more salaries. Or conversely, the less people I have, the less it will cost me, but the more time it will take. And in this specific case, I might also be bound by a few constraints. So I can't employ an infinite number of people, for example. The project must be ready in Y days, whatever that number is. It can't cost more than Z pounds. And if I employ more people, I have to pay them less to make sure that I don't surpass that Z pounds value, while also keeping within the number of people X. So as you can see, things can get pretty complex very fast. So what is my priority? A fast conclusion or the cheapest outcome? Or somewhere in between, which is a balance between cost and time. And this is where optimization modeling can really help immensely to reduce uncertainty and cut down the time taken on the decision process. So, of course, all of this can be done manually or by reasoning things out. But what if I have many more objectives or many more constraints, right? So by doing it mathematically, you can speed things up immeasurably, right? Especially as your optimization gets more and more complex. Also, having automated optimization also works great if you have to run the same kind of optimization repeatedly with slightly different constraints or slightly different objectives every time. And you don't want to keep repeating the same exercise over and over again using pen and paper, really. So any questions before I move on to the next slide? I can't see the chat. Rachel?
Can't get myself off mute quickly enough. Apologies.
It's all right.
So I've got a couple of things on the chat. So we have a number of different processes, some of which happen at the same time and some are one after the other. Can we use optimization to find the best operating conditions in our case?
Yes, in that case, that is a classic case of using optimization, actually. So you can have any number of processes. So this is just one process. I have a sorting process, but that sorting process might be followed by a packaging process. It might be followed by a shipping process, or the sorting process is happening in parallel with a production process, for example, or another production process. And as long as you can describe whatever that process is, so for example, things like throughputs, things like you know what your inputs are, you know what your relationship between your inputs and outputs is, right? You can join those processes up, so to speak, right, into one larger model, and you can then use all of those variables or use optimization to optimize all of those variables as a flow-through process. Yeah, so yes, absolutely.
A question about the initial data. So I assume you need an initial data set, but do you have guidance on what size it should be if my assumption is correct?
Yeah. So yes, this one varies a lot, actually. So generally, you do need an initial data set, and I'll explain in a couple of slides, actually, in a few slides further along this presentation. And that initial data set could be large, could be small. Obviously, the larger the initial data set, the better your optimization probably will be, because you're covering more of your knowledge space. You know, you more possible combinations of inputs and outputs. But yeah, it's good to have a data set, but it's not always absolutely necessary. It really depends on the kind of optimization that or the process that you want to optimize, rather.
Okay, thank you. Can these techniques be used to find the optimum set of variables from a large, complex data set?
Yes. So absolutely. So if you have a large complex data set with a lot of inputs, a lot of outputs, and not just, let's say imagine you have a 2D table, right? A flat table. It doesn't mean just the number of rows, which is large, but also the number of inputs and outputs on each row are many. And that's okay. Yeah, you can use optimization algorithms, and there are various which can be used in this case to actually find what your optimum set of conditions should be, if you know what your outputs should be, right? And it doesn't have to be a specific row on that data set, of course. It can be interpolated within that data set, and to a certain extent, sometimes slightly outside of that, of the area that being covered by that data set. Yes.
Okay, I've just put a little thing in the chat to ask for some more, but I haven't got anything else at the moment.
Okay, thank you. So I'll dive into a couple of examples. So the first one is about complex rostering. So let's pretend I am in charge of rostering for a company which employs 54 staff members, and the company works 24/7 with staff working on 4 shifts. So morning, afternoon, night shift, 8 hours each. Day shift is 6 hours, straddling part of the morning shift and part of the afternoon shift. So we have a number of different constraints. So there must be a minimum number of people on each shift, and the number varies per shift and day, depending on the requirements of the company. The staff are full-timers, which means that they must work at least 36 hours per week, but they cannot work on more than 5 days per week. More constraints: no one can work the night shift immediately followed by a morning shift, as otherwise that would mean that would they be working 2 consecutive shifts. And some people have taken some vacation leave over the next week, and some of the staff prefer to work specific shifts over others. So the number of constraints has started to add up. So as you can see, not only is this not a trivial problem, but this also needs to be done every week, because you need to tell your staff which days and which shift they're working. So what if we had a specialized algorithm where we can just enter all the rules as specified, we click run, and then just get the results back? Now, this doesn't mean that all the rules will be satisfied all the time, because sometimes the rules may be too restrictive or too conflicting. And that's when the user would need to start choosing which rules are important, or giving different weightings for different rules, for example. So in any case, I did take this example. I did use a specialized algorithm to run the described rostering optimization. And as you can see, the number of staff assigned on each shift is the minimum required, except for the day shift on Monday, right? Highlighted here in red, to which 5 people have been assigned instead of 2. But this is okay, as 2 was the minimum required and not really the maximum number, and needed have to be 2 exactly. So that constraint was absolutely satisfied. One other constraint was that each staff member had to work at least 36 hours over not more than 5 days per week. So as you can see in this table, all staff members have been rostered to work between 36 and 40 hours, great, as required. And if we take 4 staff members as an example, they all have 2 days off per week, which may or may not be consecutive. But that maximum of 5 working days per week has been satisfied as well. We also had some staff requirements. For example, Emily Johnston couldn't work the night shift on Monday and the morning shift on Tuesday. And in fact, she hasn't been assigned those shifts. Don Harper couldn't work the day shift on Tuesday, and he hasn't been assigned that either. And he prefers morning and day shifts, which he has been assigned, which is great. So similarly, Mario couldn't work the day shift on Wednesday, and Chris Campbell prefers afternoon shifts. And this is the only type of shift he has been assigned over his 5 working days. So in this case, the rostering has been satisfied to all the rules that have been implemented, that have been specified. Now, what if we change the rules a bit? Because Chris Campbell's home situation has changed recently, and he doesn't mind working other shifts now, for example, right? So once we take that rule out and rerun the optimization, we can see that there are some changes to the total number of rostered staff. So for example, the day shift on Monday has gone down from 5 to 4, while the Saturday day shift has gone up from 5 to 6. But that's not the only change. So for example, the assigned shifts for Chris have gone from only afternoon shifts to a variety of shifts, morning, afternoon, and night. Even the days that he's working has changed. But however, on the other hand, other constraints, such as those for Emily, Emily's vacation leave, have still been maintained, which is great, which is what we were after. And we can actually also see a change in the number of hours being worked by various employees. So, which means that they are working various day shifts, right? As the day shift is 6 hours long and the other shifts were 8 hours long, with some employees increasing hours. You can see, for example, Timothy Chapman on the top row going from 36 to 38, whereas Don Harper has gone down from 38 to 36 hours, right? So the rostering has actually changed, and it's not just a matter simply of changing one person's roster. So now imagine extending this to hundreds of employees, right, with multiple rules related to different people. And this would be pretty much impossible to do manually. And in fact, all of this rostering optimization was done in Python using a specialized package called PyWorkforce. But there are other solutions out there that we could leverage too, from AWS and others as well. It could even be set up through a custom interface for your companies, where you enter all the rules simply, and every staff member gets an email with their weekly roster automatically. And they might get, so all the graphics that I showed, for example, the weekly roster and shift roster for each member was generated by myself. I built as part of the optimization code. I wrote such that you get the plots being generated so that to easily show who is working when, right? So all of this can be done through the partnership with Smart Vision as well. And as you can imagine, this approach can be extended to scheduling of services, not just rostering as well. So how is this an optimization? So in this case, the loss function can be equal to 0, right? So if all the constraints are satisfied, and we have n constraints, whatever those are, so if all the constraints are satisfied, then the loss is 0. If one or more of the constraints, right, from 1 to n, whatever n is, are not satisfied, then the loss is greater than 0, meaning that the optimization has either not converged yet, or there actually is no solution because there are too many constraints, or the constraints are conflicting. So what the optimization algorithm will do, it will either continue trying different combinations of, or different permutations rather, of variables until it reaches a loss of 0, or else it will just tell the user, look, this is the best I can do. Not all constraints have been met, and the loss is whatever the number is, greater than 0. Okay. So this is an excellent example of where we can reach a loss of 0 for a very common problem, essentially. I mean, rostering is something that is done, globally across, hundreds of thousands of different companies, I'm sure. So, any questions on this topic before I move on to the next example?
I haven't got any new ones.
Okay, that's fine. So the next example is about optimizing for time and price. So imagine you work in a manufacturing environment and you need to formulate a product by combining a number of different ingredients. But it gets a bit interesting. So you need to combine 3 ingredients, one each from 3 groups of ingredients, and I'll show this in the next slide. And each ingredient has its own associated price, time to process, and stock constraint. And the blend actually has to have a combined weight of 225 plus or minus 1 kilos. So how would you go about optimizing the perfect blend? So these are the 3 groups that I mentioned, right? And we need to combine 3 ingredients, one each from groups 1, groups 2, and group 3, right? So if we take group 2 as an example, there's no obvious choice which ingredient to choose. For example, if I choose ingredient E, right, it costs the least, but it takes the longest to process, 1.55 minutes per kilo. But if we choose ingredient C, it costs 6.5 times as much as ingredient E, but on the other hand, it takes less than half the time to process. So which one should I be using in this case for my formulation? So in this optimization problem, we need to optimize the balance between price and time. So in this case, we are minimizing something. That's our optimization objective. We need to make sure that the batch size is correct. That's a constraint. And we need to ensure that only one ingredient from each ingredient group is used in any batch. So this can actually be thought of as 16 variables, right? So we have 8 variables, and this is the quantity of each ingredient being used. and the other 8 variables are whether that ingredient is being used or not. It is a 1 or a 0, right? So if it's the quantity multiplied by 1, that I am using that ingredient by that amount, or if it's the quantity of ingredient multiplied by 0, I am not using that account. This means that there are 3 more constraints though, because we need to use only one ingredient from each group. So the sum of A plus B being used is equal to 1, and so on and so forth. Because if I'm using A, that's a 1. If I'm using B, that's a 0, then it's a 1. If I'm using D but not C and E, again, that's a 1, right? And so on and so forth. So you can think of it as having 16 variables, which is not a trivial problem. So if you think about this, there are obviously a vast number of possible combinations this could take, right? So remember, it's not only time and price, but also which ingredient is used from each of the 3 groups, and the total batch size must be equal to 225 kilos. So we therefore need to run an optimization. So we need to minimize the time and price while keeping within the constraints. And as I mentioned a bit earlier, when doing any optimization problem, we need a loss function, right? And remember, a loss function is a calculation which we come up with, really. There's no universal loss function that can be used. And with this loss function, we'll be calculating how much the formulation will cost us, right? Not just in terms of price, but also time. So in this case, this is a possible loss function, right? So the lower the price and time, which will depend on which ingredients are being used, the smaller the loss. We can also bias this loss towards price or time by setting a weighting. So for example, if price weight is 10, but if price weight is 10, but time weight is 1, right? This means that we want to reduce the price more, so price is more sensitive than time to us. And time is not actually that important, because if the price weight is 10, as soon as the price goes up slightly, the loss is going to go up by much more than if time had to go up, if time weight is just a value of 1. So what I did is I ran this optimization problem using a Bayesian optimization approach as follows. So 10 initial random points within the specific constraints. Then I ran the optimization for a further 140 points, right? So, and each optimization step was evaluating hundreds of different samples to select the next one based on which samples would fill in this 16-dimensional. Remember, we have 8 plus 8 variables, 16-dimensional variable space best. And then the end of the optimization, we selected the best 20 options out of the total 150 points. So why this approach? There's a large number of variables, as we mentioned, 16, which means that the number of permutations is very large, and hence it would require quite a large number of iterations to come to a minimized loss, as we'll actually see in a later slide. And Bayesian optimization is a much more modern approach to this problem. And we can, using Bayesian optimization, we can actually reach minimum loss quicker than with other algorithms. And I actually also tried other algorithms, and they actually didn't work. Bayesian optimization was the only one that worked in this case. So what did the optimization look like, right? So in this case, you can see the cost is going down over the first 40 iterations or so, right? With only very small improvements after that at this rate over here and over here. We could, of course, have put a conditional stop, right? So meaning that even if we specify that we want to run the optimization for 150 iterations, if the cost doesn't differ by a specific value, whatever that might have been, after, let's say, 10 iterations, then the optimization would have been stopped. In the previous example, I mentioned that the loss value could be down to 0. In this case, it will never go down to 0. It doesn't go down to 0, and it will never go down to 0, because loss was a function of price and time, and any formulation we make will always have a price and time cost associated with it. So in this case, we're not trying to match a number or a set of numbers, but we're trying to find the global minimum. Now, if we explore the best 20 iterations of these 150 iterations, we can explore and find out what they look like. So this is a plot that I generated with the results that I obtained from optimization. You can see time versus price. And we can go over and hover over each point, and it will give you what the cost is, which is the function of the price and time. You've got the price and time in themselves, and you've got how much of each ingredient you're using in the formulation. So in this case, you're using ingredients B, E, and G with a very small quantity of G, right? So in this case, this is the maximum cost, almost 40,000 using B, E, and G. This is the minimum cost and using B, E, and H ingredients. Again, if you hover over all of them, you'll see that there's only one ingredient being used from each group in every formulation. So this case, it's a very easy visual way of looking at the results, and then you can select the ones that you think will work best for your specific situation when it comes to actually manufacturing this batch, right? Again, this is custom built, and which could also be built for your cases. So what if now let's take this a further step, right? So what if we had to make 3 consecutive batches, right? All with the same constraints and the same ingredients. This would mean that this is now a 48 variable problem, right? Because it's 16 variables per formulation times 3. And there's also the added complexity that individual ingredient stocks are limited. Remember that we didn't have an infinite amount of ingredient stock for any of the ingredients. So the optimization would either simply take too long to be feasible, or else it would fail as there would be too many constraints. And in this case, it did fail. I did try to implement a Bayesian optimization approach, and actually it just wouldn't run. There were too many constraints in this case. So in this case, what we did was we took a more of a brute force approach, right? Where we generated thousands of different random samples, right? Which is sometimes can be useful, but it does mean that we do leave finding the best options down to mere chance, right? So statistically, the more samples we run in this case, the more likely we are to find the best options. But that could mean running thousands and thousands of iterations. So as an example, right, comparing the best, right, in other words, the ones with the lowest cost after 500 and after 50,000 iterations, you can see that the results are quite different, right? However, the constraints are met every time. So each batch is 225 kilos, which is what we required. There's only one ingredient used in each of the formulations, and the stock quantity of each ingredient was never surpassed over the 3 formulations, right? So if you add these up, you never went over the maximum stock available. The results are quite different, though. For example, in this case, after 50,000 iterations, the formulation with the lowest cost, right, was not only considerably lower than the best one found after 500 iterations, but it's only using, for example, ingredient G from group 3. Whereas in this case, the best one was the best combination of formulations was using ingredients F and H. So obviously very different results here. And so in this case, we're generating tens of thousands of samples in this case, right? But completely at random, within the constraints, but randomly. So if we had to look at the minimum cost from all the permutations carried out from 500 to 50,000 iterations, we can see that we had actually found the minimum after 10,000 iterations. Beyond that, there were no other permutations which gave a lower cost, right? Now, how do we actually explore all this data? This is a lot of data that we've just generated. So, but we can actually also explore these results using a more graphical medium. So this is a parallel plot. It looks very busy, and it is, but it's actually very simple to interpret and explore, and you can get a lot of insights from these kinds of visualizations. So over here, what you've got, ingredient 1, formulation 1, name and quantity, ingredient 2, formulation 1, name and quantity, and so on. So 3 ingredients for 3 formulations, which is what we were after. Then you've got the overall price, the overall time, and the calculated cost, right? So then you can start exploring which ones work best. So for example, if I want to find only the ones with the lowest cost, these are the best 10, for example, right? I can see that the ones with the lowest cost actually have the lowest price and a medium range time. And if I want to explore them further, I can see that they are quite different, actually. They're not all following the same trajectory, so to speak. If I want to explore by price, for example, I can see that the ones with the lowest price, as we saw, give the lowest cost, but medium range time. But if time is actually more important to me, I can explore the ones that give me the lowest time. So the cost is actually a bit higher, and the price is mid-range. It's not at the lower end of the scale again. And obviously, but again, the trajectories are quite different. So this is a really easy way of visualizing a lot of inputs, a lot of outputs, and you can really focus on what you want. Which will then help you decide which of these options you actually want to go ahead with. So when I started this example, I mentioned that when we tested out the first optimization, right? So just one formulation, so a single set of 3 ingredients, we used a Bayesian optimization approach, and we ran the optimization for 150 iterations. And that I chose a Bayesian optimization approach because it can find the minimum in many less iterations than other techniques. In the second part of this example, we used a random sampling approach, right? And in fact, we needed many more iterations. So we said the minimum was found after 10,000 iterations to find the minimum, right? But these cases weren't exactly the same, right? So in the first part, we only had to optimize one formulation, whereas in the second part, we had to optimize making 3 formulations from the same stocks. So what if we did actually a direct comparison? And this is what I did. So these plots show the best 20 iterations from both the Bayesian optimization here on the left and the random sampling techniques for the exact same scenario, that is optimizing one formulation only. So in both cases, as I mentioned, the results are after 150 iterations. And the results we get are actually very different. So as you can see, the ranges of both time and price are very narrow for the Bayesian optimization here on the left, right? So 302 to 316, 122 to 129, really, 123 to 129. But they're very wide for random sampling after 150 iterations, between 150 and 425, and 190 and 310 for time, right? So obviously, in this case, we're not focusing anywhere near the minimum for sure. So also the overall cost of the best 20 iterations varies a lot for random sampling, right? Between 49 and 84,000 in this case, but it's very narrow and smaller actually for Bayesian optimization as well. So the Bayesian optimization is obviously much more efficient, right? It's focusing on finding the minimum much quicker. And in fact, the random approach required almost 19,000 iterations to reach a comparable minimum cost, right? 38,400 versus 30,300 here. To reach a comparable minimum cost, and with actually no guarantee that minimum would have been found ever, really, given that we are doing random sampling with some constraints. Yes, if you do tens, hundreds of thousands of iterations, probability will tell you that you will find that minimum, right? But we actually don't know when we will have found that minimum at all. So it's a lot to take on, but I hope that really highlighted the power of using optimization and using focused optimization, not just random sampling, which is probably just to see if you find the minimum. And if there are any questions, I'm happy to take on any other questions, Rachel.
I've got a couple, yeah. So when you're deciding the right method, so Bayesian or linear, do you tend to do that based on the problem at hand, or do you test these different methods?
It's a bit of both. So usually you start off with an educated guess, right? So yeah, you do have to understand the problem at hand, absolutely. Not all optimization techniques will work for all problems, that's for sure. And in this case, as I mentioned, for example, I did try other, known techniques like gradient descent techniques, for example, and they didn't work for where the Bayesian optimization did. So you would have an idea of which ones would work best, but you probably need to test one or two out before making your final decision. Absolutely.
I have another one.
Yep.
Can I use another interface as a solver, e.g. an Excel plugin with advanced formulas in it to resolve these constraints or cases? So,
Yes, you can. Excel actually now has a Python plugin. So you can use Excel as the interface, the main interface, and Excel is great because everybody is familiar with Excel, and people aren't scared of using it as much as you would with a completely new interface. So yeah, definitely, you can do some coding within Excel as well. That can be done using Visual Basic in that case. But so yeah, there are various options, absolutely. That could be something that can be discussed when we get to, for your specific use case. But yeah, definitely.
okay, thank you. I haven't got any more at the moment.
Okay. So with that, I will hand over to John, who will describe a selection of use cases.
Thanks, Robert. Yeah, I'm just going to just take a few minutes just to wrap up. There are lots of use cases, and what we've done here is just given you a non-exhaustive list in different kind of sectors and industries. Interestingly, at the top there, Robert already talked about product formulation. That was one of his examples, and his other example was a rostering example. And I think actually there's a kind of there's an abstraction here when you look across industries that, we're often looking to optimize, people, processes, products and things, whichever way we look. And supply chain obviously is a key area where we can optimize what is a really very complex process in various ways. But it also applies to healthcare and whether that's rostering or whether that's looking at maximizing dosages weighed against risks of other illnesses or infections. It's all based on the same premise, really. Could you just click to the next slide, please, Robert? Just to interesting here, pharmaceutical, for example, has drug formulation, which is very similar to product formulation, you might say, in manufacturing, but then it has its specificity, which is around what happens within the clinical trial, which of course is in effect a process. One we didn't put in here is actually something we were involved in a couple, 3 years ago, I want to say, which was around optimizing engineers within a telecommunications setting, going out and fixing mobile masts and towers, which is a variation on a very famous optimization challenge, which is called the traveling salesman problem. How do you optimize geographically where folks are in order to solve problems, and some problems are more important than others. So yeah, so there's lots of different use cases, and everybody here has a different, comes from a different industry or is looking to different problems. So one of the things we're very interested to do, as Robert said, is to have conversations with you to see whether optimization is a good fit for the challenges that you're looking at. So yeah, could you click to the next slide, Robert? This also then links to the conversation actually we just had and the question we just had about Excel. I think as everybody is aware, a lot of what goes on today in data science and optimization is done in Python. Robert mentioned that a lot of the work that we do is if it's around rostering, it's using the PyWorkforce library. There are many other ways in which you can code solutions to these problems in Python. But there are, a little bit like Excel, there are some powerful kind of no code / low code, as they say, ways to do optimization. There are a couple of IDEs, for those people who haven't heard the term, develop interactive development environments which help you generate code. Probably two of the more famous ones are from IBM. There's something called Cplex, and Gurobi have their own. They're both commercial. MATLAB is another for those people who've known or heard of MATLAB. Python itself, which of course is open source, has some, slightly higher level interfaces that allow us, to develop optimization solutions if we're not pure coders. So all of those things exist. And then there are, in a sense, more abstracted versions of these things, which are, in a sense, less techy, more operational faced, more operational planning based on users who are not necessarily going to write code or crank IDEs. So here's an example. This is open source. This is a company, an organization, I should say, called Optiplanner. And they make open source, which is particularly good at the resource planning side of optimization. So, stuff like employee shift rostering, which again was an example that Robert looked at. And this is a kind of a visualization of, how you might do this in a browser in real time as, situations change. So if you're in a call center and you want to roster within the call center, which agents are online at a particular point in time. What you don't control is the demand. You don't control the calls that are coming in and the types of calls that are coming in. So this is an example where there's an optimization engine sitting underneath, and as the situations, the scenarios change in real time, the optimization does its stuff. And the schedulers can use a visual interface on top of what is essentially a very complex optimization engine underneath. So that can include all sorts of scheduling. It could be timetabling, it could be vehicle routing, it could be, any of the above, really. And I've just got one more example of a visual interface. If you could just click to the next slide, Robert, please. Which I really like. I really like the whole supply chain aspect, personally, of the optimization challenge that we have. And this is a commercial product. The last one was open source. This is a company called Ames, who deal with supply chains. And what this shows you is how you can effectively design your supply chain network, if you like, at different levels. So it's a smart business tool that allows you to optimize supply chain at the different points across the hierarchy of the supply chain. So where do you want warehouses to be? Where are the factories? Where are the local distribution centers? Where are the end retail points? And this is one of the live demos. It's a YouTube video, actually, that you can go and look at. We shared the link below that shows you, given this network, this is the best way to optimize within the geographical constraints that you have. And a little bit like, I can't show it actually because we just popped the slide, but if you go to the video, you can see you can do that hover over as well to each of the individual points and see the individual optimized parameters, just as Robert showed earlier with the scatter plot. Yeah, just next. So how might we help you in this process? Smart Vision does various, or delivers services and products in various ways. The one I would point to is probably the third one. We do increasingly these days, we do a lot more enablement. So our philosophy is we're very happy to build models for you and share them with you and service in that way. But increasingly we do a lot more enablement. So we'll work with you perhaps on a project to do your first optimization. We'll get you set up. We'll give you the skills to then potentially take that on and do more optimization yourself. So I think enablement's probably our primary focus. But as Robert says, we can develop these interfaces that we just demonstrated. We do a lot of UI development and anything related to data science and the sort of strategic decision about, is this an optimization problem or a prediction problem? Then we're very, very interested to have that first conversation to see which direction that ends up taking us in. So that's it in terms of the slides. Any further questions, Rachel? Did anything come along?
Any more that have come in? No.
Okay.
So thank you very much.
Go ahead. Yeah.
I was going to say thank you. We will, the next step for us is we get this all processed and we get the video uploaded to our website along with a PDF version of the slides. So some of the links and things like that will be active clickable links when you receive that. We'll get an email out to you as soon as we can, probably this afternoon or tomorrow morning, depends on how long it takes the video to process and upload, but we'll get that to you as soon as we can. We would love to hear from you. So if there's anything in here that's kind of piqued your interest, or you would like to have a more detailed discussion about your particular use case or how you're tackling these problems now, please do get in touch. So if you email us at info@sv-europe.com, I would pick those up and I can put you in touch with John or Robert, depending on what the particular situation is. So thank you very much for attending, and thank you, Robert and John, for your presentation. We hope to hear from you all sometime soon.
Thanks, Rachel.
Thank
Thanks,
you.
Robert. Thank you, guys.
Bye.
Bye.